So last lecture we talked about expectation, and then we used expectation to define what we call variance. So let's do a real quick review of those concepts from last time, right? So our definition of expectation or expected value was that if I had a random variable x, then the expected value of x was, well, we had two cases. If x is continuous, then expected value of x was the integral over everything of x by fx, here fx is the PDF, dx. And in the discrete case, instead we summed over everything of x times fx. And here, in the case where x is discrete, this little f is the PMF. So expectation is a really important concept. One of the things it does for us is it allows us to define what we call the variance of a random variable. And the variance of a random variable, which captures kind of how spread out the support is, how spread out the probability is over the support of the random variable, or over the whole kind of real line. The variance of a random variable, we write as VAR of x. It's defined to be equal to the expected value of x minus its mean squared. So this definition might look a little intimidating. We have kind of nested expectation, but expected value just gives us a number. So it's x minus some number, square that whole thing. That is kind of this quadratic function of a random variable, and you throw that again in an expected value. So that's variance, and we have a theorem, because sometimes that's maybe not the preferred way to calculate expected value. This theorem, which related variance to the expected value of x squared and the expected value of x. And the theorem said that if I want to calculate variance, if I know the expected value of x and then know the expected value of x squared, I can say, okay, expected value of x squared minus expected value of x quantity squared, that gives me the variance. Notice that our variance typically is not going to be 0, and so these two numbers are not going to be the same. So I can't just pull out my square, that'd be expected value. Expected variance generally is a positive number, right? We can see that because we have this square term here. And we said a while back, maybe a lecture or two ago, that if I take the expected value of something positive, I better get a positive number. And so this is a really kind of, we call this often the shortcut theorem for calculating variance. It allows us to calculate variance knowing just the expected value and the square of the expected value of the square. So expected value of x and expected value of x squared. And so today, those are kind of two really important numbers, and we're gonna talk about variance today, but then we're gonna talk kind of more generally about expected value of powers of a random variable. And it turns out that's a kind of centrally important concept in probability. Before we get to that, let's look at some examples. So let's look at an example of variance, and we had looked at some continuous cases last time, and so let's look at a discrete case this time. So my example is I'm going to have x, and it's going to follow a binomial distribution with parameters n and p. So again, this is read as x is distributed as bin for binomial, and I have two parameters in my binomial distribution, n, which is some integer, let's say bigger than 0, and p is some probability in 0 to 1. And the canonical experiment that defines a binomial random variable, let's say canonical experiment, is that if I do n independent binary experiments, yes-no experiments, let's call them coin flips, each with a probability P of a heads, then if X is the number of heads among all n of them, this is distributed binomial NP. So it's kind of, and you can think of it as coin flips or any kind of other binary experiment, yes-no experiment. So binomial random variables can take on any value. Their support is 1, 2, 3, 4, etc. up to n. So I can get 1 head, 2 heads, 3 heads, or I guess I can get 0, right? You can get 0 heads, 1 head, 2 heads, up to n heads. And we're assuming all these coin flips are independent, and then so I just count, okay, I do these n coin flips, how many heads do I have? If I have a probability P of on each flip of getting heads, and they're all independent flips, that thing has what we call binomial distribution. And we've looked at this before. We've looked at the CDF, maybe. We've definitely looked at the PMF. The CDF is not super nice for this. And if you recall that we had looked at, I think last time, the expected value of this, we had said that if X has a binomial distribution, then the expected value is just the product of the two parameters n and p. And that can be interpreted as I do n independent experiments, each with the probability p of heads. How many heads do I expect? On average, in expectation, I expect about n times p. If I do 100 coin flips and the probability of getting heads on each coin flips is 1 over 100, I expect on average to get 1 out of those 100. If I do, if I have a probability of 1/2 of getting heads on each of my coin flips and I do 10 coin flips, I would expect on average or in expectation to get 5 heads. All right, so it's just n times p. What we can ask is kind of what the variance of a binomial random variable is. And the way we're going to do it, since we already know the expected value, we can then look at the expected value of the square of a binomial. And if we can calculate that, then we have all the components. We can use our shortcut theorem up here and calculate the variance. So this is kind of how is that, how is the probability distributed over kind of the support? Probably it's less likely, it's kind of centered around maybe the expected value, and less likely as I move away from that mean. So it's going to have, eventually a binomial distribution, right? So it's discrete, so it has this kind of stick diagram, but it has kind of a bell-shaped-ish distribution. And they're actually kind of, there are connections between a binomial PMF and a normal distribution, right? Normal would be a bell shape that looked like this, and you can actually show in some cases, and we can maybe show this at near the end of the course that somehow the binomial in the limit, approaches a normal. And this harkens back, we'll see kind of when we derive this variance, this is going to harken back to an intro stats course when you talk about proportions. Okay, in any case, what we want to do is we want to calculate the variance. We want to calculate, to do that, we're going to use our shortcut formula. And so I want to calculate the expected value of x squared. And the law of the unconscious statistician says that if I want to calculate the expected value of x squared, normally what I would do is if I wanted to calculate the expected value of x, it would be x times fx. But now I want to calculate the expected value squared, so I'm going to say it's x squared times fx. And that's what we call the law of the unconscious statistician. Real nice formula, just change, instead of x, I put whatever function of x in my sum, or in the continuous case, in my integral. Okay. And let us rewrite this and input what the PMF is. So the PMF for our binomial is n choose x. That is, out of the n places, I choose x of them to be heads. I have probability p to the x of getting x heads, and then the rest of them better be tails. So I will have 1 minus p, probability given tails, on those remaining n minus x. So that's our formula. And we can place, when we calculated the expected value, if we go back and look at that, we used some tricks, and those tricks are going to come in handy again here. First of all, I can change my sum from starting at 0 to starting at 1. Why can I do that? Because if x is 0, x squared is 0, the whole thing is 0. So basically that first term doesn't contribute anything to the sum. We had also seen last time that, let me write this down here, is that if we had x times n choose x could be written as n times n minus 1 choose x minus 1. So I could rewrite my sum, now starting at 1, and I'll have 1x, but then I can change the x times n choose x to n times n minus 1 choose x minus 1. And I still have my p to the x, and I have a 1 minus p to the n minus x. And similarly, so this is kind of fact 1 we use, similarly let's make a change of variables, and we're going to, like we did last time, choose y to be x minus 1, or equivalently x to be y plus 1. So if I do this kind of change of variables, I could write my sum. What I really want is my sum to be indexed starting at 0. So if I make the change of variables, now it goes from y is 0 to n minus 1. Instead of x, I have y plus 1. I have an n. I have n minus 1. Choose, well, y now. I have a p to the y plus 1, a 1 minus p to the n minus y minus 1. And I'm going to factor out some things that don't depend on y, don't depend on my summing variable y. So for example, I can factor out this n, I can pull that out, and I can factor out one of these p's. Let's pull that out. If I do that, I'll get an np on the outside, and then I'll have a sum, 0 to n minus 1, y plus 1, n minus 1 choose y, p to the y, 1 minus p, and I'm going to rewrite this as n minus 1 minus y, right? This is using kind of similar trick as we did for the expected value. What I'm going to do now is I'm going to break up my sum. I'm going to distribute everything. I'm going to distribute this part to these two terms, and I can break up my sum. So I will have an np, and I'm going to have some big parens. My first term is I'm going to have y, n minus 1 choose y, p to the y, 1 minus p to the n minus 1 minus y. And then I'll distribute everything to the 1 here, which doesn't really do much, but I'll have my second sum, which is sum y to 0 to n minus 1. And now we just have n minus 1 choose y, p to the y, 1 minus p to the n minus 1 minus y, okay? Don't worry, it gets easier from here. We're going to use kind of two tricks we've seen before. So what we're going to recognize is that this part is the sum of a PMF, is the sum of a binomial, now n minus 1 p. So it's the sum of a PMF, right? If you write out the PMF for a binomial n minus 1 p, it would be n minus 1 choose y, p to the y, 1 minus p to the n minus 1 minus y, right? We sum that over the whole support. We know that has to give us 1. And this part, if you go back and look at your notes for or just kind of calculate the expected value, this is the expected value of I'm going to write kind of a views notation. This is the expected value of a binomial n minus 1 p. I'll write it like that, right? It's y times, this is the PMF of a binomial n minus 1 p, right? It's the same thing as this. And so that sum is just going to be the expected value of that kind of thing. And we know the expected value of a binomial is just the product of its parameters. So it's n minus 1 times p. And from there, we're kind of basically done, just some algebra. So I get np, I get an n minus 1p, and then I get a plus 1. So if you recall, we started off, this whole thing was to calculate the expected value of x squared. And I claim is that that is the expected value of x squared. The reason that we wanted this is that we wanted to calculate the variance. And the variance, by our shortcut formula, we can say is the expected value of x squared minus the square of the expected value. And so now we know what this first term is. It's np. It's not super nice. np times n minus 1 p plus 1. You could probably simplify it. We don't need to. And then the second thing is we know the expected value of the binomial is n times p, and it's a whole quantity squared. And let's just distribute things out, right? What do we get? We get n squared p squared, so that's n p p. We get a, what else do we get? np, so np squared, and then we get plus an np, so that's that first term expanded out, just some algebra, and then our last term is n squared p squared. So some of this nicely cancels. We get np minus np squared, or if I factor out my n and a p, I get np by 1 minus p. Now that's a nicer formula. And that's the variance of a binomial random variable. This might seem familiar. In intro stats, you often saw things that looked like, for example, if you looked at the standard deviation of x, which you would just define as the square root of the variance of x, this would be root np by 1 minus p. And this starts to look like formulas that we saw in intro stats. If you go back to your intro stat notes and you talk about proportions, it's not quite what you saw, but it's really close. In intro stats, the n is in the denominator there. You would get something like, you would typically see p by 1 minus p over n, and you'd see a square root. But this is highly related. You see that p and that 1 minus p, that's coming from the same place. And maybe by the end of the course, we could actually justify this whole thing. Certainly, if you take 452, you can justify where that formula comes from for intro stats. But you can see the kind of similarity there, that p and 1 minus p in the binomial. And that's because basically when you solve those proportion problems in the intro stat course, you're basically assuming a binomial distribution. Not that anyone says it. So just as a real quick recap, this is a specific example to use how to use a couple tricks, so maybe it's a little beyond what I would expect on homework or an exam. It's good to see once in your life. But again, one of the really useful tricks here is that if I want to calculate the variance, I need to know the expected value of x squared and the square of the expected value. And so kind of the expected value of x and the expected value of x squared are important. And more generally, expected value of powers of a random variable are really kind of important. It's going to kind of play the role of polynomials in, say, algebra and calculus, or power series in calculus, second semester calculus. You're basically talking about powers of a variable. And those are very important, and we're going to see some of that today, and how powers or expected value of powers of a random variable are important. So we're going to define what is called the moments of a random variable. So here's our definition. If we have some integer r, so r is a positive integer, natural number, 1, 2, 3, 4, etc. We define what we're going to call, the rth moment of a random variable x. And we're going to define it as, so the notation is typically mu sub r. And mu sub r is the rth moment of x. So let's just kind of denote that. The rth moment of x that is mu sub r, and it is defined as the expected value of x to the rth power. So that's our definition. So moments of the random variable are just expected value of powers of that random variable. You know, we've already seen some examples of this. Mu sub 1, which often is just denoted as mu, is the expected value or the mean of the random variable. Mu sub 2 would be the expected value of the random variable squared. We saw that mu1 and mu2 together can give us the variance. But you could also, you know, talk about mu3, which we haven't really seen, but you could talk about it. It would be the expected value of the cube. And, you know, you can imagine more examples. So these are called the moments of the random variable. And we have actually seen quite a few examples because, so let me just maybe give another quick example here. If I have a binomial NP random variable, we had seen that the expected value, let's write it this way, we'd seen that mu1 was the expected value, which was NP, and we had seen that mu2, which was the expected value squared. We just calculated that, and that had some horrible formula. What was that horrible formula? Nothing too nice, but it was NP, n minus 1, P plus 1. Right. We've seen this for called the exponential distribution with that lambda. We had seen the expected value. We had calculated the expected value squared to get the variance. We had seen that that's doable. And moments are kind of a third major way of understanding random variables. Fairly loosely, the collection of all my moments is going to more or less, I'll be a little bit vague here, it's going to kind of characterize my random variable, right? So the first moment tells me kind of where the thing is located, kind of the center of the distribution. If I add on the second moment, that's going to start to tell me something about how it's distributed around that mean, or specifically the variance is going to tell me that, but that's some kind of combination of the first two. So those first two moments in some complicated way encode kind of where the distribution is, how kind of spread out the probability is over the space. The third moment might tell me, starts to tell me something about how skewed the distribution is. And you can imagine that you have more and more and more of these moments. They become kind of harder and harder to interpret what they mean. But if you kind of collect enough of them, or if you collect an infinite number of them, you're really going to kind of characterize the distribution in some sense. Another way that these random variables, these moments are going to be important is that they're related to what's called the moment generating function. So this is a bit of a weird beast. Let's give a definition, and then I'll tell you why I think it's important, and we'll see in this course why this moment generating function can be important. So, definition. Moment generating function. And this is typically denoted as MGF. So we've seen so far, we've seen the CDF, which we first saw. We then saw PMFs and PDFs. So we kind of had the CDF view of the random variable that told us something about it. Equivalently, we could talk about the PMF or PDF. And the third kind of major way of talking about the random variable is going to be the MGF. So we kind of have three different ways of characterizing or knowing everything we want to about the random variable. Turns out, if you know the CDF, you kind of know everything about the random variable. If you know the PMF or PDF, you kind of know everything you need to know about the random variable. Or equivalently, if you know the MGF, you kind of know everything you want to know about the random variable. And depending on the problem, either the CDF, the PMF or PDF, or the MGF are going to be the easiest way to kind of show things are true or calculate things about my random variable. So the MGF is going to seem a bit of a mystery, but it's going to it's actually a very useful third way of encoding information about your random variable. Okay, let's not delay anymore. If I have a random variable, so x is a random variable, then the MGF of x, let's say, is a function, and typically that function is denoted with m for MGF, and it's a real valued function. So it's going to take in numbers, and it's going to spit out real numbers, okay? So the MGF is some function, and it is defined, the way we define this function, for if I pick some real number, typically we use the letter t as our number, we define m of t as the expected value of e to the t x. Okay, so this is our definition of the MGF. It is a function of a number t, any real number. Could be 0, could be 1, could be pi, could be 1/2, could be 1,000. It's a function of this number. Takes in this number, and it spits out another number. What number is that? It spits out the expected value of e to the tx. So let's just back up. The expected value is just a real number, right? The mean of whatever random variable we're looking at. So it takes in t, spits out some expected value. Takes in a real number, spits out a real number. The number it spits out is the expected value of e to the tx, right? If I'd said e of x, I think people would have known what that means, kind of had a sense. But e to the tx looks weird and kind of scary. But it's just a function of x. I could have said, log of x, or x squared, or the cube root of x, right? There's just functions. And we have a formula following our theorem, our law of the unconscious statistician, that of how to calculate this, right? And so let's just put an aside here. Let's say for a discrete random variable, m of t is the expected value of e to the tx, which is what? Well, we sum over our support, over all of our x's, whatever they are, and normally we'd sum x by fx if we wanted to calculate expected value, but instead we plug in e to the tx. So that's just a sum that hopefully is easy to calculate. In the continuous case, of course, it looks kind of similar, but instead we get the integral of e to the tx times now the PDF fx dx. And so it's actually not so bad. It's a certain expected value, right? It's either the sum of e to the tx fx or the integral of e to the tx fx. Notice that it is always a function of t, right? So when I change my input, I'm not changing x, I'm changing t, right? I sum out x, or I integrate out x. So if I plugged in m of 2, would be the integral e to the 2x fx dx, etc. Right? A kind of technical note about this is that expected values, of course, don't always have to exist. This is one of the reasons I pointed this out earlier. And so it's possible I could plug in some value for t where this expected value doesn't exist, either because the integral or the summation doesn't converge. And so kind of more technically, this moment generating function is going to be defined for some interval, we should really be more specific, some neighborhood around 0. So there'll be some values. Of course, if I plug in 0, I just get what? I get 1, right? E to the 0 is 1. Expected value of 1 is 1. So it's always defined at 0, but there's typically going to be some, right? So there's going to be some kind of neighborhood around 0 where this thing is defined, but it's possible if I plug in values of t outside my neighborhood, it might blow up. It might not converge. But that's okay. We're just going to define the MGF for wherever it converges, and that's going to be some neighborhood around 0. Kind of technical point. We'll see why that can come up, but it's not too scary. Okay. Let's look at some examples of what the MGF does, and then we'll start to make some cases for why this is an interesting function to look at. Because right now it just seems kind of obscure. Okay. Let us go back to our continuous, kind of favorite continuous example. And that was where x had an exponential distribution with some rate parameter lambda, right? So lambda here is some positive constant. And our definition of an exponential random variable is to have this PDF. It's continuous. And the PDF lambda e to the negative lambda x for positive x. Implicit in that is that for 0 or negative x, the PDF is 0. So the support of this thing is positive. Has non-zero density for the positive numbers. Okay. And we could calculate for this what the moment generating function is. The MGF is the expected value of e to the tx, which looks kind of weird and scary, but not so bad, right? We're going to integrate e to the tx fx dx. And of course, I only have to integrate over the positive numbers because my PDF is 0 for negative numbers. We get e to the tx, and for the positive numbers, our PDF is lambda e to the negative lambda x dx. And this is actually not too bad of an integral. Let's bring it down here. This is going to be, well, let's just kind of combine some things. It's integral 0 to infinity. Pull out the lambda, why not? We have e to the, looks like t minus lambda x dx, right? And that's an integral actually we know how to solve, right? T is just some number that's fixed. Lambda is another number that's fixed. X is our dummy variable in our integral. We have to be a little bit careful in this case. So let's say if t is bigger than or equal to lambda, then e to the t minus lambda x. So certainly if t is equal to lambda, this whole thing is 1, because that becomes t minus lambda becomes 0, the whole thing becomes 1, and you get the integral of 1 over some infinite interval, and so the integral will not converge, it will blow up. But more generally, if t is bigger than lambda, then let me write this. Let's say if we look at t minus lambda, that thing is positive. And so if we look at the function of e to the t minus lambda x over values of x, this thing looks kind of like this. It's a positive number here. This thing is bigger than or equal to 0, and so it's this exponential function. And the area is going to blow up. So the area is infinite here. So in this case, this integral is actually not going to converge. The area under the curve is infinite because it's kind of this exponential function. We're just going to get an infinite value. If we try to integrate this thing, it doesn't really converge well. Okay, so we should try to avoid, so this is where I was talking about how this expectation might not always exist. If, however, t is less than lambda, then we're going to be okay, because in that case, t minus lambda is less than 0. And if we were to plot e to the t minus lambda x against values of x, it would look like this. And in this case, this area is going to be finite. So this is going to be a finite area. It's basically e to some negative value x. So it's going to decay as x gets large. We're integrating from 0 off to positive infinity, and so that will converge. So in this second case, let's just bring this all the way down here, right? We had the integral 0 to infinity at lambda out front, e to the t minus lambda x dx. Now it's actually not so bad, because that is going to converge nicely, and we can kind of treat it like the limits were not infinite, but they were finite, right? If I had an integral a to b, what would it be? It would just be, we would have a t minus lambda in the bottom, and it would be e to the t minus lambda up top, right? X, and we evaluate this from 0 to infinity, right? That's the antiderivative. We evaluate at 0, at infinity and 0. So we get a lambda, we get a t minus lambda, and then we're evaluating e to something negative. So again, this thing is negative. As x goes to infinity, this top goes to basically 0, right? It's going to become e to the negative some really, really big number, or 1 over e to a huge number. Right? So that goes to 0. And then we subtract off, and we subtract off 1. And so we get negative 1, or you could rewrite this as lambda over lambda minus t, where I've switched t and lambda and canceled that with a negative 1. And that's the integral. So that is this integral for, so let me write this out. This is, of course, what we're calculating was m of t, our moment generating function. M of t here is equal to, in this case, lambda over lambda minus t, as long as t is less than lambda. So this is what I was talking about, is that there's some interval around 0, some neighborhood of 0, for which this then converges and works nicely. And so we just define the MGF in that interval. If you try to take t bigger than lambda, you're going to run into issues. But we just say, it's not defined there. Okay. And that's the MGF. So that's a nice kind of concrete example of the MGF. We'll see a lot more of these in the coming days. They're kind of fun to calculate, and they can make some problems really simple. If you know the MGF, solving the problem can be really simple. So let me start to try and make the case for why we care about these MGFs. Right? We've seen what they are, and we have this example, at least one example. And the name of the function, moment generating function, somehow implies that it's related to the moments of our distribution. And indeed it is. Indeed, it can be used to generate the moments of our random variable. So hence the name. The moment generating function is going to allow us to generate the moments of a random variable. Let's look at how that works. So let me just rewrite my MGF. My MGF for my exponential is lambda over lambda minus t for t less than lambda. Okay. And this is a real valued function. And in this case, it's a differentiable function on my interval. As long as t is less than lambda, I can take the derivative in that case. So let's consider taking derivative of this function. Let us look at dm dt, right? You take the derivative with respect to t. It is a function of t, not a function of x, a function of t. So we take the derivative with respect to t. And you can forget what this thing means, how we derived it. This is just a Calc 1 problem. Lambda over lambda minus t. What's the derivative of it? It should be lambda over lambda minus t squared. Low d high minus high d low, etc. Right? let's look at dm dt at 0. What's the derivative? What's m prime of 0? What's the derivative of m, of our moment generating function, at 0? This is going to be lambda over lambda squared, or more simply, 1 over lambda. Recall, for an exponential random variable, the expected value of this exponential random variable is 1 over lambda, and the expected value squared, go back to notes last time, whoops, was not 1 over lambda squared, but 2 over lambda squared. So if you don't believe me, go look at how we derived this last time in the notes. So if I take my moment generating function, I take a derivative, and I plug in 0 into my derivative. So I look at kind of m prime. Another way of writing this is m prime of 0. Right? I get, suspiciously, I have generated the expected value, or the first moment. Let's try this trick again. Let's take the second derivative of m. And I'll let you do the Calc 1 problem. It's going to be 2 over lambda, lambda minus t cubed. That's the second derivative of my moment generating function. And so if I look at m double prime of 0, that is, if I look at d squared m dt squared at t is 0, what do I get? I get 2 lambda over lambda cubed, or 2 over lambda squared, which is suspiciously the second moment of my random variable, the expected value of x squared. So what's the general theorem? You can probably guess it. Here's the theorem. Pretty easy to write, kind of one line. If I take the rth derivative of my moment generating function, evaluate it at 0. So another way of writing that is m r of 0. Rth derivative evaluated at 0. This is the rth moment of my random variable, which you might denote mu sub r. Really simple to write out. Nice. So if I give you the moment generating function m, from on a high, I come down from the mountain, and on stone tablets I have inscribed this moment generating function. And I say, tell me what the rth moment is of this random variable. I don't tell you anything else about the random variable but its moment generating function. All you have to do is you take r derivatives of that function and you evaluate it at 0. And that will give you the rth moment. So this moment generating function has encoded in it somehow the moments of the random variable and can be used to generate those moments. Turns out that this moment generating function, again, as I said before, kind of tells us everything we need to know about the random variable. The CDF is one way of viewing the random variable. The PMF and PDF give us another view of the random variable. And the MGF is a third view. None of these seem like they're kind of, I mean, there's some connections between them. CDF, PMF, okay, you know, MGF, you know, PDF kind of thing. There's some relations between these. But it turns out they're all kind of characterizing the random variable pretty much fully, using in different ways. And so depending on the problem, one way or another is going to be the easier way to solve that problem. And the moment generating function, which seems like this kind of weird beast, encodes the moments of the random variable, which kind of encode information about the distribution. In fact, they encode basically all the information about the distribution of the random variable. So this theorem, actually, I can make some kind of heuristic proofs of it. Maybe these aren't the most formal proofs. I'm going to pull a couple moves when I prove this. but it gives some insight into why this is true. Because as a brute fact, this seems mysterious. Why I define this thing that's the expected value of e to the tx, and then I take derivatives of it and I plug in 0, and somehow that gives me the moments. It seems very arbitrary, but it's actually kind of really intimately related to some kind of Calc 2 facts about power series. So let's just kind of look at this. I'm going to present kind of two ways of thinking about it, and then wave my hands in some places where I don't want to go into all the details, because this is not an analysis class. It's kind of a probability class, obviously. So consider the rth derivative of my MGF, right? So that we can write as dr dtr, and my MGF, of course, is the expected value of e to the tx. And let's just do this in the continuous case. The discrete case is not going to look very much different, but continuity is kind of slicker. The continuous case is slicker. In the continuous case, this expected value is the integral of e to the tx fx dx. And I'm going to pull a move, an illegal move. Call the police. I'm going to interchange my integration and my differentiation. So there is a certain amount of what we call regularity that needs to be true, and you would talk about this in kind of maybe a graduate level analysis class. It's a little bit beyond scope. You talk about maybe a bit in Calc 2 about when you're allowed to, say, interchange differentiation and infinite sums. But if I'm allowed to do this, so all of my functions are nice enough, I can push my derivative inside the integral. And I'll put a little star here to say that, yeah, technically need to justify that move. If I can do that, I then have the derivative of the rth derivative of this thing in here, which is e to the tx fx. Now fx actually doesn't depend on t, so you can actually kind of pull it out. Really, it's, right, fx doesn't depend on t. It's a constant as far as the derivatives is concerned, and so you get the rth derivative of e to the tx. What's the rth derivative of e to the tx? Well, let's just calculate some derivatives. Let's say d dt of e to the tx. All right, what is that? Well, I pull down an x. All right, derivative with respect to t, so x is just some constant, right? And so I pull down the constant. That's a rule for differentiating exponentials. Let's do d squared dt squared of e to the tx, which is, of course, d dt of x e to the tx. This is a derivative with respect to t, right? X is a constant, so that can certainly come out. It's x times d dt of e to the tx, and we pull down another x. So you get x squared e to the tx. In general, you could just keep playing this game. You could actually prove this by induction. In general, if I look at the rth derivative, d dt to the r, dr dt to the r, e to the tx, I'll end up just pulling down x r times, and I'll be left with e to the tx. Okay. That's a useful fact, because I can now write this integral as the integral. The rth derivative of e to the tx is x to the r, e to the tx, and we have an fx, and we have a dx left over. So remember, we started off, this is the rth derivative of, let me actually just rewrite that here, right? This is the rth derivative of my moment generating function. So we can write it in that way. And so certainly, if I take this rth derivative of my moment generating function and I plug in 0, integral x to the r e to the 0x fx dx. Of course, e to the 0 is 1, so I can pretty much remove that. That leaves me with x to the r fx dx, and you look at that. It's the expected value of x to the r, which was what we call the rth moment. So that's a real cute little proof of what's going on. And basically it's relying on kind of two facts. One, I have enough regularity or niceness of my functions that I can switch differentiation and integration. So that's a theme that if you take 452, you will see that all over the place. And as long as things are nice enough, you can do that. And then it relies on that derivatives of e to the tx are nice, and that they just kind of pull down copies of x. So that the relation between the moments, which is x to the r, and e to the tx, which defines our moment generating function, is that derivatives of e to the tx pull down, it's going to be x to the r. It's going to bring that thing down there. So that's the relation. It's that through kind of derivative relation, we get these powers of x. So that's one way of showing this. And I think there's kind of a second cute way of showing this. And the second cute way is using power series in some way. And so the hand-wavy way, let's just write this out, is that we can expand a function as a power series, right? So normally you can write fx as, and it's some infinite power, infinite series with some constants out front, right? But it's basically an infinite degree polynomial, right? Any kind of what we call analytic function, or any kind of nice enough function, as long as the function is kind of infinitely differentiable, you can always expand out any kind of function as a power series or a kind of infinite degree polynomial. And so the analogy is that powers of x tell us something about function, tell us about a function, and so powers of e, the expected value of powers of a random variable, tell us about a random variable. So if you normally have some kind of function, if I want to kind of totally characterize a function, I can just look at, I need to know something about the powers of, how to combine the powers of x correctly in power series or Taylor series, right? Analogously, I can kind of know everything I need to know about x if I look at expected value of powers of x, where x now is a random variable, instead of being a function where I can know everything about my function if I know something about my powers of x. A little less hand-wavy way to look at this is that if I look at the power series of e to the x, recall what the power series is. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. Right? That's the power series of e to the x. And so if I look at e to the tx, I can say this is 1 plus tx plus t squared x squared over 2 factorial plus t cubed x cubed over 3 factorial plus ... right? Where I'm plugging in now x is a random variable and I have a multiplier t there, right? And if I look at a derivative of this thing, then what am I going to get? Well, the 1 goes away. Derivative with respect to t, I'll just get an x out front. I'll get a 2 t x squared over 2 factorial plus etc., right? if I were to look at instead, say, the second derivative, I would take another derivative. My x goes away, my 2's cancel, and this t goes away. I would get like x squared plus dot, 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 right? So derivative, the first derivative tells me kind of about x and then some stuff. Second derivative, x squared and some stuff. And so if I were to look at, say, d dt of e to the tx, and if I could push that derivative in, so I could say it's the expected value of the derivative, then this would be like the expected value of x plus, and if I plug in 0, it's like 2 times 0, x squared, blah, blah, blah. But everything else would, if I plug in 0, go to 0. So what I would get left with at the end of the day was just e of x. Okay, I'm moving a little fast, kind of hand waving a little bit. But you can play the same game. You could say if I look at second derivative of e to the tx and I push that inside, right, this would do something like this. What am I going to be left with? It's going to be the expected value. If I plug in t is 0 here, this is going to be the expected value of like x squared plus what amount's going to be 0, right? And that's going to be first one would be the first moment, this would be the second moment, right? So it's kind of another way of looking at it, right? And so that is kind of relating that to power series, right? And that's, I think, really kind of the more fundamental thing that's going on here with moments. Okay, a little beyond the scope of this course, but it gives you some sense of why we care about this moment generating function, right? So if we go back up, it's a bit kind of mystery of a definition. It's the expected value of the tx, but that thing is going to be related. Derivatives of that are going to be related to the moments. In fact, we can generate the moments of this MGF by taking derivatives, or generate the moments of the random variable by taking derivatives of it. So that's this kind of theorem that we had here. And it's kind of related. It plays the same role where powers of x, you have a whole collection of powers of x, and you know all the moments of the random variable, and they kind of characterize the random variable, and that's kind of related to how powers of you can characterize any function by knowing powers of that function, or powers of infinite degree polynomials, powers of x. Okay, it's enough kind of analogy, but I think the MGF is weird enough you want a little bit of a background of what's going on. Let's look at, in this case now, it's actually a discrete example of an MGF. So we looked at continuous, and let's go back to where we started this lecture. And we started this lecture, we had we were looking at binomial random variables. And nothing I've said about MGFs pretty much restricts them to continuous. They exist in the same way, and that theorem, that derivative theorem, is true for discrete as much as it is true for continuous random variables. So we can generate, in this case, let's generate the moment generating function of a binomial. So that is the expected value of e to the tx. But now in this case, it's discrete. And so we have a sum. Of course, our support for a binomial goes 0 to n. And it's the sum e to the tx, so the integral of e to the tx, times the PMF, right? And what's the PMF? The PMF is n choose x, p to the x, 1 minus p to the n minus x. It's the PMF of a binomial random variable. Okay. And so let's see if we can kind of simplify this thing. What can we do? Well, we have something power of x, right? So I can group this like this. I could say it's e to the t to the x. And then we also have p to the x. So you could group these together. And let's do that. Let's say it's n choose x. And then we have p e to the t, the x. That's just some algebra. And 1 minus p to the n minus x. We're going to abuse our binomial theorem. So let me just remind you what the binomial theorem is. As an aside, binomial theorem. I think we talked about this kind of briefly before. Not something I would expect you to memorize, but it's useful to know, right? And we said that if I write a plus b to the n, this is, you can expand this as a sum. I goes 0 to n of the binomial coefficients, actually named after this theorem, n choose I times a to the I, b to the n minus I. So the binomial theorem, right, if I look at a plus b to the n, it's some polynomial, right? And you can write out that polynomial. It's a polynomial in a and b to various powers. And they have coefficients. It turns out the coefficients are exactly the binomial coefficients. And then we're going to have to combine the different powers of a and b. And this is the way to do it. So you can use this theorem in two ways. You can say a plus b to the n, expand it out, or in this case, you can go backward. You can say if I have something of this form, by sum of binomial coefficients by something to some powers, where the powers always sum to n. So in this case, n minus x plus x sums to n, or I plus n minus I sums to n. I can go backwards and say that is equivalent to a plus b to the n. So in this case, I can reverse my binomial theorem. So I'm going to kind of use this thing and say that this is, so in this case, this a is basically this thing, b is this thing, and instead of I, I'm using x. But other than that, it's exactly how that theorem looks, and so I can write this as pe to the t plus 1 minus p all to the power n. That's really nice and elegant, and that's the MGF, right? That was m of t. So maybe let's just write that out and box it for binomial. The moment generating function of t is pe to the t plus 1 minus p all to the power n. All right, now the MGF is a function of t, and it's a continuous function of t. It doesn't matter that this thing's discrete. The MGF is still a function of t, and it's still a continuous function of t. It's actually an infinitely differentiable function. It's a very nice function. And so we can play around with our theorem. Our theorem says if I wanted to generate the moments of a binomial random variable, right? Recall that the first moment, expected value of x, was np. Ooh, and you're going to make me try and remember the second moment of this thing. The second moment of this thing was something horrible, wasn't it? I think it was, oh boy, let's just go way back up and look at what this second moment was. It was np, scroll back up, np times n minus 1 p plus 1. And I suppose you'd expand it out a little bit. What does it give you? It gives you n squared p squared minus np squared plus np. N squared. Yep, I think that's right. And, okay. We had this theorem that says, instead of actually doing all this integrals, if I knew my MGF, I could just take some derivatives, right? So my theorem said that if I looked at dm dt at t is equal to 0, that gives me my first moment, right? That is, okay, so what's dm dt? Derivative with respect to t, right? d dt of pe to the t plus 1 minus p to the n. I got a little chain rule action going on here. N pe to the t plus 1 minus p, and then you take the derivative of the inner, which should just give me pe to the t. That seems right. And I want to evaluate this at t equals 0. So I'm going to plug in 0 for t, n, p times 1, e to the 0 is 1, plus 1 minus p. p times e to the 0 is 1. Well, we got p plus 1 minus p in the middle. Of course, we knew it had to come out to be np, and indeed, the algebra comes out to be np, right? Which we said, if you believe my theorem, there's always expected value or that first moment. We can do the same game. We can look at the second derivative, dm dt squared, which is, of course, d dt. We already know what the first derivative is. It is what? It's n p. Ooh, I'm going to call me on this. There should be an n minus 1 here, shouldn't there? Turns out it doesn't matter in this case because we had 1 to the n minus 1. Bring down my n, and I have that middle part, right? Okay, sorry, that's correct now. There's an n minus 1 up there. So my first derivative is n p e to the t plus 1 minus p to the n minus 1 p e to the t. It's not so nice. We have to do some product rule to get this derivative, right? Okay, let's just do it out, right? Derivative of the first times the second plus the second times derivative of the first, right? So n, derivative of the first one, brings down n minus 1, and then it goes p e to the t plus 1 minus p, now to the n minus 2. Derivative of the inner, which is p e to the t, and then we multiply by p e to the t one more time for the product rule. And then we have to add the derivative of the second one, or let's say the first, which is n p e to the t plus 1 minus p, like that, n minus 1. Just product rule, but kind of messy. And then derivative of the second one, of course, is just p e to the t. Doesn't change. And this is kind of a mess. However, when we plug in 0, evaluate this thing at 0, a lot of these terms are going to drop out, right? What are we going to be left with? N times n minus 1. I'm going to get p times 1. Let's just write it. P times 1 plus 1 minus p to the n minus 2. And then I'm going to just get p times 1 times p times 1 plus n times p times 1 plus 1 minus p to the n minus 1 times p times 1. Okay? Lots of things are going to simplify, right? Because this thing is 1 and this thing is also 1. And so what we get is n by n minus 1 times p squared, 2 p's, plus np, which gives us, let's just expand it out a little more, n squared p squared minus np squared plus np, which is exactly what we had said our second moment was, right? That's mu2, that's our second moment, right? N squared p squared minus np squared plus np. N squared p squared minus np squared plus np. So the theorem is true, and it's true for the continuous, it's true for discrete, it's just generally true. So that's one nice feature of MGFs. We'll see at the very end of this course, hopefully by the end of this course, the goal is to, kind of in the very last lecture, to prove what is called the central limit theorem. So the central limit theorem is something that you might have come across in an intro stats course. It talks about means. And by the end of this course, you will be able to understand the proof of the central limit theorem that says it's kind of this really important theorem in probability and statistics. And this course will give you all the tools to kind of understand the proof of it. Turns out, the most straightforward way to prove it is using MGFs. And so MGFs can generate moments, but they're going to have more kind of deep fundamental importance as we go through the course. So we'll see kind of near the end of the course how these things can be super useful and make proving theorems really straightforward. So proving the central limit theorem without the MGF, really hard. With the MGF, doable. So it's a really kind of important tool in our tool belt of probability. Let's talk about some other kind of theorems. we had talked about, what happens if I look at linear transformations of random variables, what happens to variance, what happens to expectation. So if I have constants, let's say constants a and b, we're going to find another random variable y, which is let's say ax plus b, right? We talked about how the expected value, we could kind of just push through nicely, and the variance had a little more complicated rule. You had to square the a and you got rid of the b. So moment-generating functions are defined in terms of expectation. Expected value, variance is defined in terms of expectation. MGFs are defined in terms of expectation. And so the question is there a similar rule for MGFs? And indeed there is. So turns out, so if we have constants a and b, y is ax plus b, then if I look at the MGF of y, so m sub y, here's the MGF of y of t, we can derive it in terms of the MGF of x. So this is the MGF of y here, so sub y. That is going to be equal to e to the bt times the MGF of x, let's say mx of at. I'm going to put this in the box. It's super useful. So my is MGF of y, and mx is MGF, what am I writing? Let's say MGF of x, right? And they're related. If I linearly transform x to get y, then MGF of y is e to the bt times the MGF of x, not evaluate the t, but evaluate the at. And this is a theorem that is within our pretty straightforwardly within our realm of proving. And it follows pretty directly from the definition of the MGF and our theorems about how expectation behaves. So the proof you could almost write in one line. My of t is expected value of expected value of e to the ty, which we can write as the expected value of e to the t. Well, y is ax plus b. And we can actually kind of separate things out. Let's use some exponent rules. This is e to the atx times e to the tb, right? That's just rules of exponents, grouping things in different order. And exponents say if I add, if I have a sum and an exponent, I can write it as a product. And e to the tb is a constant as far as his expectation is concerned. It's not a random quantity. And so I can pull that out of my expectation. I can pull that e to the tb out, and I'm left with the expected value of e to the atx. And e to the atx is exactly the MGF of x, not evaluated at t. The MGF of x would be, right, mx of t would be expected value of e to the tx. So the expected value of e to the atx is MGF evaluated at at. So that's just using that fact, and that's the proof, right? That's what we claim. The MGF of y, we can just kind of write it as e to the tb times the MGF of x evaluated at at. So that's a very useful theorem that will show up definitely in homeworks, could show up in exams, that kind of thing. Nice, and it's kind of, again, what happens when you linearly transform something. We know what happens with expectation, we know what happens with variance, okay, what happens with moment-generating functions. Okay. And the kind of last major theorem, which we're not going to prove, but I've made this claim, and so let's formally write it down. is that if we have two random variables, x and y are random variables, and the moment generating functions of x is equal to the moment generating function of y. For all t in some neighborhood of 0. So again, it's kind of this technical condition. They don't have to be equal everywhere, but if there's some neighborhood around 0 where these things are equal, if the MGFs are equal, then x is equal in distribution to y. So again, this notation equals with a d over it is equal in distribution. So what this theorem says, and we're not, it's definitely beyond the scope of this course, but what the theorem says is what I've claimed. If you know the MGF, you kind of know all there is to know about the random variable. So there really is a kind of third pillar of how to analyze these random variables. Yeah, so if the MGFs are equal, then the random variables are equal in distribution. So you could look at the PMFs or PDFs, you could look at the CDFs, you could look at the MGFs. They're all telling you this, fully characterizing the random variables. They're full, telling you everything you need to know about the distribution, but in different ways. And so depending on your problem, one or the other might be more useful to use. Okay, so that kind of wraps up the lecture today on moment generating functions. And that's kind of the last major topic here. What we're going to do now is, so just as kind of a review, we talked about expectation variance, we talked about definition of moments, moment generating function, we related moments in the moment generating function with this theorem, and then we saw some examples, and we had this theorem, these kind of last two theorems. For the next couple of lectures, we're just going to start introducing a whole bunch of different types of random variables. So now we've seen a bunch of ways of characterizing random variables: CDFs, PMFs, PDFs, expectation, variance, moments, moment generating functions, etc. And we've seen a couple different types of random variables. We've seen some uniform ones, we've seen exponential, we've seen binomial. There's a whole world of random variables out there, and we're going to just go through some of the common ones that are kind of important to be aware of. I don't really expect anyone to memorize anything for an exam. Memorizing distributions is fairly useless, but it's good to kind of see a whole kind of collection of them. And there's this whole kind of universe, this pantheon of different distributions out there. And so we're going to go through, for the next couple lectures, examples of many different types of distributions: discrete distributions, uniform distributions. And there are different ways that the probability can be distributed over the numbers. And when we go through these, we're going to look at, okay, what's the PMF, what's the PDF, what's the CDF, what's the MGF, what's the moments, etc. And so what that's going to do is going to be a real nice review of all of these concepts. We're just going to basically introduce some distribution and work some problems on them. Deriving CDFs, PDFs, relating MGF, moments, etc. Okay, well, we're going to stop there for today's lecture.